Okay, here's question 6, November 2016. Hydrogen gas reacts with sulfur powder, sulfur solid, according to the following balanced equation. Hydrogen gas plus sulfur goes reversibly to hydrogen sulfide gas, delta H is less than 0. The system reaches equilibrium at 90 degrees. Okay, before we go any further, first of all, look sharp. Here is a solid. Remember that solids have no place in your equilibrium constant calculation. Okay, and then as well, look, this is the forward reaction is exothermic, and 1 mole plays 1 mole, so pressure changes won't affect this equilibrium. But this solid is something to watch out for. It can't be in the Kc calculation. Okay, define the term chemical equilibrium, the stage in a chemical reaction where the rate of forward reaction equals the rate of reverse reaction. Learn that. How will each of the following changes affect the number of moles of hydrogen sulfide at equilibrium? The addition of more sulfur. This one is a solid. It is not going to affect it. So this one should be stays the same, remains the same, stays the same. Okay, let's make it say remains the same. Okay, an increase in temperature. Use Le Chatelier's principle to explain the answer. Okay, so let's say here, let's make sure we make everything in short, sharp statements. An increase in temperature, favors the endothermic reaction. The reverse reaction is endothermic. So an increase in temperature favors the reverse reaction. This means the moles of hydrogen sulfide will decrease. Okay, so we're going to write decrease at the beginning here. So for 4 marks, we must make sure we have an answer. We must have stated what the increase in temperature is going to do. It will favor the endothermic reaction. We must have identified which reaction is endothermic, that is the reverse reaction. So the increase in temperature is going to favor the reverse reaction, and this means the moles of the product, hydrogen sulfide, will decrease. The sketch graph was obtained for the equilibrium mixture. Okay, here's your sketch graph. A catalyst is added to the equilibrium mixture at T1. Redraw the graph in your answer book. On the same set of axes, complete the graph showing the effect of the catalyst on reaction rates. So if we have a look here, we need to redraw this. Okay, you know I can't draw in here. So we need to redraw this and then make a change from T1. The first thing you must notice is that this is a reaction rate graph. That's why these lines are together. The forward reaction and the backward reaction are here at equilibrium. So what is the job of a catalyst? A catalyst increases the rate of reaction for both the forward and reverse reactions. So we need an increase here. Okay, so it's going to go up and then it will return to equilibrium at a different rate. So it will return to equilibrium where the both lines are parallel at a different rate. So have a look here. This is from the memo. It shows you here. Here's the initial part. Then it goes sharply up because the catalyst increases the reaction rate of both the forward and the backward reaction. So make sure you've got the solid line and the dotted line. And then it's not going to increase forever. It will reform an equilibrium. So then it forms the two horizontal parallel lines at a higher reaction rate. So that shows you the reaction rate is increased. Low reaction rate without catalyst, high reaction rate with catalyst. Notice that this is not a concentration graph. The concentration graph would be different. That's why you have to always look at the reaction rate graphs and the concentration graphs separately. So this is the correct answer for that. Okay, now let's go to the calculation part. The first thing I saw when I looked at this is that this calculation is 9 marks. Usually these calculations are 7 marks. So if there's 9 marks, there must be another step in here. Initially 0.16 moles of hydrogen and excess sulfur are sealed in a 2 cubic decimeter container and the system is allowed to reach equilibrium. An exact amount of lead nitrate solution is now added to the container so that all the hydrogen sulfide gas present in the container at equilibrium is converted to lead sulfide. This is lead sulfide, according to the following balanced equation. Lead nitrate plus hydrogen sulfide goes to lead sulfide plus nitric acid. That's interesting. The mass of the lead sulfide precipitate is 2.39 grams. Calculate the equilibrium constant for this reaction, this reversible reaction. Okay, so what we can do is we can start out and start trying to get as many marks as we can from what's obvious. So let's put the two things in here. Okay, the hydrogen gas in here. Now remember, now we are ignoring the sulfur in our equilibrium concentration calculation because it is a solid. We don't put the solids in. Okay, let's take the volume here. We know we're going to need this for the equilibrium concentration, so we're going to divide by 2 over here. And then we know our initial, okay, there's the ratio. I'm jumping all over the place here, sorry. 1 mole is to 1 mole from the coefficients of the balanced equation. And then we know the initial moles of hydrogen are 0.16. And this is a product, so this has to be 0. And there's nothing else that it's told you here. Okay, from the initial part of the information, you can't fill anything else out in this table. You can, if you want, go ahead right now and make your Kc expression. Okay, so Kc equals the concentration of the products. What were the products? Hydrogen sulfide. Okay, over, make sure it's over, not divide, the concentration of the reactants, which is hydrogen gas. So that's going to be our Kc expression when we get to that. We can write this in here now because it's already going to get us a mark. Okay, so now we've sorted out a Kc expression, we've sorted out the table. Our job now is to find the equilibrium moles of hydrogen sulfide. Okay, because we know we got rid of the hydrogen sulfide with the lead nitrate. That's what all of this is telling you. This part over here, okay, is telling you how they got rid of the hydrogen sulfide. Took out all of the hydrogen sulfide in this other chemical reaction. So how would we find out how much hydrogen sulfide was taken out? We would have to look at this balanced equation. Okay, so we know it took out hydrogen sulfide. The hydrogen, all the sulfur in here got converted to meet up with the lead to form lead sulfide. So if we know how many moles of lead sulfide we formed, from the molar ratio we can go back and find out how much hydrogen sulfide we had. So let's look at this lead sulfide. So if we're going to do any calculation with this, we've got mass here. So we're going to use N equals M over M. Okay, M over big M. Okay, so we're going to need to find the big M for this lead sulfide. So we don't use lead much. You're going to have to hunt it down in your periodic table. Lead is 207 and sulfur is 32. So this is going to equal 239. Okay, so we can then find the number of moles of lead sulfide. Make sure you label your calculations nicely so that whoever's marking you can tell exactly what your calculation belongs to. So the number of moles of lead sulfide is going to be M over M, and we know how much lead sulfide was formed. It was 2.39, and this is divided by 239. Oh, look, we're on the right track here because these two numbers, you can see they have a nice mathematical relationship, and that should give you 0.01. Let me check in my calculator. Yep, I have 0.01. So there's 0.01 moles of lead sulfide. So now we need to go and have a look. We want to actually find hydrogen sulfide. Okay, so we're going to go molar ratio PBS to H2S is 1 is to 1. Set this out more nicely than me. I'm running out of space. These ratio things never line up for me. So how many moles? So there were 0,01 moles of hydrogen sulfide. Okay, so we now know how many moles were at equilibrium. Okay, because it was at equilibrium, then we added the lead nitrate. This produced lead sulfide, and the lead sulfide was taking out the hydrogen sulfide. So once we knew how much lead sulfide there was, we could figure out how much hydrogen sulfide was there at equilibrium from the molar ratio. So now we know that this 0,01 here of hydrogen sulfide is the number of moles at equilibrium. So because hydrogen sulfide is a product and it started with 0, this change is going to be 0,01. And the molar ratio of these two is 1 to 1. So this is also 0,01. So, but this is going to be subtracted. This is going to be added. Okay. So my equilibrium moles of this is going to be 0,15. Okay, it's going to be 0,16 minus 0,01, which equals 0,15. So there's my equilibrium moles. And then to find the concentration, we're going to have to divide this by 2, because remember, right at the beginning, I put this as the size of the container. So this should be like, it's 0,075. I nearly did mental arithmetic and did it wrong. This is 0,01 divided by 2, which is going to be 0,005, I do believe. Yeah, okay, let's make this the right size. Okay, so now we have equilibrium concentrations, which we based from finding from the molar ratio here. So let's go back to our Kc expression. Kc equals the concentration of hydrogen sulfide, which is 0,005 over the concentration of the hydrogen, which is 0,075. So let's find our value for Kc. 0,005 divided by 0,075. I've got here 0,067. This is the Kc value that I have as a final answer.